Good afternoon, everyone. Hope you are safe and healthy. On behalf of ISMN students, I welcome all the participants to the sixth day of Limit Camp. Today's student lecture is the continuation of the lecture given by Harshul Khanna on the topic geometry groups. I welcome him back to continue the lecture. Over to you.
Hello everyone. Let's continue the topic of geometry group theory. I'll share my screen. Yeah, I hope it's visible. So basically, I plan to first of all recap what we did in the last part of yesterday, the Cayley graphs part, the construction, the basic observations, and then move on with our topics. All right. So what we did yesterday was we wanted to associate a geometric object to a group, right? And we saw that we can do this through actions of the group, but a group G acts on itself through left multiplication. So we get an action that we get that G is a group of symmetries of G as a set, but since we want a geometric object, we wanted more structure to our set, right? So that's why we turned to graphs and metric spaces. So now we saw that let me scroll back. So basically we defined what graphs are, and then some what are the automorphisms of a graph, and then the action of a graph on a sorry action of a group on a graph is basically an action of group, a normal action of a group, plus it preserves the structure of the graph. So that's encoded in the fifth point here, that if the endpoints of E are V and W, then the endpoints of G dot T are G acting on V and G acting on W. And we saw some examples: Sn acting on Kn, Z mod 3Z acting on the infinite tree with valence 3. And we turn to Cayley graphs. So basically, now we come back to the topic that we want that our group should be seen as a group of symmetries of some geometric object. And we do someone is waiting in the lobby, by the way. And we do that just a second. And we do that through the object we constructed, Cayley graphs. So I'll go through the construction once. So the construction is very simple. I want to construct a graph, so I want to give you vertices and edges. So my vertices, let me start writing here. Sorry. Excuse me. Something is wrong with this. I'll just a second. Right. So the construction is simple. So my vertices are elements of G, which is the group, and my edges, and with the, so first of all we have a, let me just tell you the settings. So G is a group. S is basically a generating set. So edges are directed from G to GS for all G comma G, G belonging to G, S belonging to S, and they are labeled by S. So basically we want to connect all those edges which are one multiplication away by a generating element. So for example, suppose this was an identity element and this was a, so this was a this was an element of the generating set S, say S1, and suppose this was a generating element called S1, S2, not a generator, just a normal element of the group. Then you get this edge, then you get this edge. This is labeled by S2, this is labeled by S1, and suppose this is G. Suppose you have GS inverse, then you get a edge in this direction by by the label S. So GS inverse into S is equal to G, right? So this is the construction. Let me see if I mentioned anything before. Yeah, we just saw the examples after that, right? Right. So for example, suppose I want to construct the Cayley graph of Z with respect to 1, the generating set 1. Then I have these vertices. This is -1, this is 0, this is 1, and this is this. So this is connected by here. All edges, so there is only one generating element here. So there is only one label, so we need not use, we may not even use any label since there is only one label to be used, right? So we need not differentiate between edges. So yeah, if you had to use a label, you can just use one, and so on. Note this somehow resembles your real line, though not exactly right now. We want like the real line has some extra structure onto it, which is the distance between points. So I'll tell you the distance. So how do we define distances in graphs? But for now, just note that this resembles the real line. What about the same z but with a different generating set? Suppose I take 2, 3. Now here you have say -2, -1, 0, 1, 2, and so on. So I need two edges, right? Two types of, so I use blue color for this, and we'll decide the color for that later. So -2 to 0 is 1. This is labeled by 2. So I'll not label as it to as such, but I'm just using blue color for the 2 label. -1 to 1, 0 to 2, 1 to 3, whatever. And for 3 part, right, I'm using the red color. That would be -2 to 1 in this direction, -1 to 2 in this direction, and so on. So the Cayley graphs looks like this. These not are exactly the same. These two graphs are not isomorphic, but they are same in some sense. In the sense that if you suppose zoom out from the scene, they roughly look the same. So I'll not define that notion right now, but there is some notion of equivalence between these graphs. Observation, right? So suppose I start with E, I go to S1, observe this graph. So S1 labeled S1, so this is S1. Suppose this is labeled S2, this will be S1, S2, and so on. And I arrive at, this is labeled Sn, and this is S1, S2, multiplication till Sn. Now, note that suppose G was equal, suppose there exists an edge path from E to G, the identity element, to your element G, which is a random element in your group. And this edge path must have some labels and orders, right? Because we are essentially labeling the edges. So suppose in order, the labels were S1, then S2, then till Sn. Then from the diagram above, it is clear that G is indeed equal to S1, S2 multiplication till Sn. And for the other way around, suppose G was equal to some multiplication of your generating element, suppose S1 till Sn. Then there exists an edge path from E to G, from E to G, which has these labels in order, right? These labels occur in this order exactly. So this is just the construction of that edge path. So we observe that there is a one-to-one correspondence for each word of this form, a word in generating elements. there exists an edge path, and for each edge path there exists a word of this form, right? So there is a one-to-one correspondence between the first set is edge paths connecting E to G, and the second set is words. Uh, second words in your generating set representing your G, such that their value is G. So at any time we can, so this is a geometric object. This is your algebraic. So anytime we can go from here to here or here to here. And remember this one-to-one correspondence, we'll use it a lot. Sorry. Right. So why we introduced calligraphs was to show that the group of symmetries uh, of this graph is exactly G. So we want to show that the automorphism of this graph is exactly G. So this map should be an isomorphism. So G goes to phi G. And what is this phi G? Because we have G acts on your Cayley graph by left multiplication. So left multiplication. So each vertex, suppose you have a vertex V, this goes to GV. So we are defining G dot V to be equal to GV. Since V is an element of the group here, Cayley graphs are the vertices of Cayley graphs are your group elements. So this multiplication is well defined. So G dot V equal to GV, that's how we define the action. This is the left multiplication. So for example, suppose you had, right, let's go to the Z example, right? So we want to show that, so I'm claiming that Z acts on this graph here, suppose I take an element M, I can just translate here. So what is G's? So there vertices were, so G is M here. Just a second. M group operation is plus actually. This is Z with a plus group operation. So M plus V. So all the vertices are translated by M. So suppose I draw the picture just here. So this will be M minus 1. This will be M. This will be M plus 1 and so on. So indeed, G acts on your Cayley graph by left multiplication, but we do not know that all the automorphisms of the graph are of this form. So we want to show that the group of symmetries of the graph are exactly this group. So G acts on the graph by left multiplication, and do we need something from it? Yeah. So we showed the action on vertices. What about the edges? Well, edges, the action on edges is automatically defined because of the axiom of the group operation that it preserves adjacency. So suppose this was E, it was connecting V and W. Then G dot E is connecting GV and GW. So there exists a unique edge between V and W. There exists a unique edge between GV and GW. So this G dot E is the unique edge between GV and GW. Right. Now let's go back to the theorem. We want to prove that this map is an isomorphism. So there is only one natural map here, G to phi G. So first of all, since we have this action, and with some more some more work, basically the definition of the extended definition of our group action, which we covered yesterday. So we know that this map is a homomorphism. This we know. Now, what we need to prove for it to be isomorphism is it's bijective. So we want, first of all, to show that this is injective. Why is it injective? For that, we have to show that the kernel is phi. Kernel are the elements that map to identity on the other side. So the kernel is phi. What is kernel? So G such that phi of G is equal to identity here. Identity here is the identity function because it's so it fixes every element. It's equal to identity. So uh, what does so phi of G is a function, right? It should be identity. So phi G of E should be equal to identity of E because these both are functions. What is phi G of E? Because G is basically acting by left multiplication. Phi G of E is GE G dot however you may this is a uh, sorry, just a second. E is the identity element here, so I should not use E. I guess I should use one because my edges are also represented by E. So this is one. This is also one. So phi g of 1 is equal to G times 1, which is G group operation 1, which is equal to G. And identity of 1, just since identity fixes everything, this is equal to 1. So that implies G is equal to identity element. So that means the kernel is trivial. No non-trivial element fixes all the elements. Hence kernel is phi. That implies injectivity. Third, surjectivity. This is the more important part. We want to prove that every automorphism is of this form, right? So our setting is suppose phi belongs to automorphism of the graph. Look at this map. So we will take a phi here in a range, and we want to prove there exists. We want to prove there exists G, such that the image of that G in this map is essentially your phi. So phi G is equal to phi. So we want to find a G such that phi G is equal to phi. Now, how do you get that G first of all? Now, note these two both are functions. These are the symmetries of a graph, right? This acts by left multiplication, and this is just a random automorphism of a graph. So since these both are functions, so let's observe what phi does to the identity element. So it has to be some group element, right? So since it's the automorphism of the Cayley graph, the identity element has to be sent to some group element G. Some vertex, since vertices are group elements, it has to be sent to some group element. So suppose phi of the identity element was equal to G or G naught. Then we claim that phi is equal to phi G naught as functions. So we want to prove they agree on every vertex. So this function agrees on every vertex, and this equality holds in every vertex and every edge. But note, since edges are determined by your vertices, that because of the group action definition and automorphisms, we just need to check. So enough to prove that phi and phi g agree on vertices. Of course, they agree on the identity element. That's how we constructed the G naught here, because phi G naught of 1 will be just equal to G naught group operation 1. That will be G naught. So these two agree here. But how do we move to more elements? So basically, we are here right now at the identity element. Sorry, the identity element, and we have moved and we show that phi agrees here. Now we want to move to your other element. So this suppose this was S1 belonging uh, to your generating set, then this will be an edge. We want to show now for S1, then for S1, S2, and so on. So notice what we are doing here, right? First of all, we proved for one, then we are proving for these vertices which are one edge away from there. So that's how we come to the notion of, let me actually scroll back to to the previous day slides here. Word length. So in G with respect to X, how do we define word length? This is have I defined here before? I must have. Right, here it is. So a word length is essentially this only, right? So this is one far away from the identity element. This is two edges away from the identity element. But we want to make this notion precise in an algebraic way. So what is a word length? So word length, uh, once we have one way, suppose we have a one way, say algebraic way of doing it, we can translate it to a geometric way, and if you have a geometric way of doing it, you can translate it to the algebraic way. So how do I define word length? So word length is essentially, so what is s1 s2 for example here? So word length of uh, g with respect to your generating set s, the shortest sorry, the shortest the length of the shortest edge path between the identity element and G. So for example, S1, if S1 belongs to your so length of S1 would be equal to 1, length of S1 S2 would be equal to 2, because the shortest edge path is here is 2, unless S1 S2 belongs to your generating set. And here we allow, with respect to S union S inverse, we take inverses too. So for example, in your example, let's go back to our example z and 2 comma 3 here. What's the length of 1? Well, 1 is just 3 minus 2, since we are allowing inverses. So 3 minus 2 is 1. So no, so 1 is equal to 3 minus 2. That implies length of 1 is equal to 2, right? We need two elements of the generating set to describe your element of the group. So length of 1 is equal to 2 here. But what about this example? Well, 1 is equal to 1. That implies length of 1, since 1 is a generating set here. 1 has a group element here, 1 has a generating set here. Length of 1 is equal to 1. Right. So the idea of word length should be clear to you. Now, first of all, how does this translate to your algebraic sense? This is the geometric sense that it's a shortest edge path between 1 and G. Uh, how does it translate to your algebraic sense? That it's the smallest n such that G can be represented as S1 till Sn. So the smallest n such that G can be represented in this form. Of course, we are allowing plus minus, the powers to be plus minus 1, since we are allowing inverses. Right. Then let's move on to the proof of surjectivity. So that's what we set out to do. So basically, why we defined word length was, since we have proven this result, the surjectivity, that both functions agree. So we have to prove this. Both functions agree on vertices. We have proven this for 1. We want to move to word length 1. So these are all of the form S1, and then we go on to word length 2, then 3, and so on. We cover all the group elements. So this is basically induction on word length. Suppose length of vertex was equal to 0. We have already shown for in like this case, that means v is equal to v is equal to identity element. Phi of 1 is equal to g naught. This is by definition, because we suppose that phi 1 is equal to g naught, and this is equal to g naught times 1 is equal to phi of phi g naught of the identity element. So phi 1, so both these functions agree on the length when the length is 0. What about now? Suppose this is true. Suppose this holds for length less than equal to n. So this is just a procedure for strong induction. For now, we have to prove for length equal to n plus 1. So suppose we take v to be the vertex. So length of v equal to so suppose we have length of v equal to n plus 1. What do we want to prove first of all? So to prove phi of v is equal to phi g of v, right? So since the length of the v, the length of group element V, also a vertex, is n plus 1. So that means V is of the form W type S, where W belongs to a group. This is just a group operation, and S belongs to your generating set, and length of W is equal to n. So this has length n, and since we are multiplying one element, so this corresponds to the fact from going from S1 till S1 S2. So this was your V. So this was your V. This was your W, and this would be your, the H label would be your S, right? So V is of the form W into S, where W belongs to G, S belongs to your generating set, and length of W is equal to n, right? So first of all, what do we know? Uh, we know that uh, since length of W is equal to n, by induction hypothesis, we know this is equal to phi g of W is equal to G. This is equal to GW, right? Right. Now note, what do we have here, right? Uh, so this is the, so this is our, now first picture I'll draw is the original tree. Here I'll draw the picture of your, just a second, I'll scroll down a little bit. Here so this is our original tree. This is the tree, sorry, original graph. This is graph after action of 5G. So first of all, here, what do we have? Whatever is happening here, you have this W, you have this V, and there is an edge S going on here. So since that means is equal to WS. What happens here? So here it would be, so there exists some edge GW, and now W and so GW and there exists an edge between GW and GWS, right? By definition. This is by definition of the Cayley graph. So GW is an element of a group, GWS is an element of the group. Since they differ by one generating set element, this is S. So these both are unique edges in this sense. There exists a unique edge coming out of W with label S. This goes to V, and here there exists a unique edge from going from GW, which is equal to phi G of W, with label S. So this goes to phi G of W times S. So since both these edges are unique in that way, that means so phi G of, when we apply this image here of phi G, this vertex must essentially go to this vertex. So phi G of V is equal to phi G of W times S is equal to GW S is equal to G, WS was V, so GV, right? So phi G of V is equal to GV. Sorry, no, phi, my bad. We are applying phi here. So we were applying so graph after the action of phi. But since we had that phi of W is equal to phi G of W, so this is correct. So since we had that, this one, phi of W equal to phi G of W equal to GW, right? And so here we had phi of W equal to GW, and here we had phi of W into S. This is not, and this is hence equal to phi G of W into S, because W had length less than equal to N, and we applied the induction hypothesis. So essentially phi, when we applied phi, so this vertex must essentially go to this vertex. So phi of V equal to phi G, must equal to this one, and this is equal to this phi G of W into S, which is equal to GW into S, which is equal to GV. So, and this is equal to phi G of V. So we see that phi and phi G agree on V, where V was length n equal to length was equal to n plus 1. That implies induction is completed, and we have the theorem hence proved. So we have proven the surjectivity now, that every automorphism is of this form, that you are multiplying some element, left multiplying some element to your graph. Hence we have that the group of so what we get is the group of symmetries. So this means, so the group of symmetries of your Cayley graph. So of a Cayley graph G comma S is exactly G. So that's what we set out to do. We wanted to associate a geometric object such that its group of symmetries is exactly equal to G. So the Cayley graph is such a geometric object. Right, let's move on. Now, we have studied these calligraph construction, these how to construct a calligraph, but how? Let's look at how they look like. So, for example, one basic example is a free group. So, what's a free? A free group is basically so a free group is suppose I'm defining on two elements. It's like told you about the presentation earlier. So it's generated by two elements a comma b, and there are no relators. There are no relations between a and b. So everything is of this form. So a b b a cube b square a minus 1 b 5. So it's everything of and it can be a b a 2 a square b minus 1 a cube b to the power 5, so on. So it's of the form, every element is of the form here, a to the power p, p1, b to the power p2, a to the power p3, p power something, and so on. Or it's of the form b to the power p1, a to the power p2, b to the power something, and so on. Finitely many. Not essentially, by the way. Like it can go on forever. Like you can have something of this form a b a b a b. Right. So what's up? So that's so we are using the we want to see how the Kelly graph of F2 looks like with respect to some generating set, and we let A and B be the two standard generators for F2. So how do we construct this? So let's start. So first of all, we have the identity element, and this identity element, since there are two generators, it must be so. So let me just draw it. Just a second. So I have my so let me just state it here. I have my identity element here, right? And I have A, B, and what vertices can be identity element connected to? It can be connected to your B, it can be connected to your A, like here, here. This can be connected to your A inverse and your B inverse. So there are exactly four many vertices you can connect your identity element to, or actually any other element you can exactly connect it to your four vertices, because that's how the multiplication works, right? So given G, it can be connected to so G, so GA, GB, and this was what GA inverse, right? G inverse, GB inverse. Just let me check that. Uh, yeah, that's how it works, right? This will be connected, uh, like this will be connected with label A coming towards GA. This will going out of GA inverse to G, and the label will be A. So exactly, in general, there are exactly two times the cardinality of your generating set many new vertices you have to add, right? So we have identity element, and we connect four. Let me use a different color, or actually let me just use black. And you have to connect it, the identity element, to four different vertices. This is A inverse, B, B inverse, and blue edges represent. So the blue edges, this represents the label B. This label represents the label A. So now, what new edges are connected to your the newly added vertices? Now we have four different vertices, right? So these four vertices we have. Just a second. Now to each one, you already have one edge to each of them. There should be three more. You have to add three more edges to your new vertices, to each of your new vertices. So that's how it looks. So for example, this was A. We added three new vertices to it, and again you get these three, and you will add like this, and so on. And then to this you will add this, 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 and again to your vertices you will add, and go on adding. And what's the general procedure? We can just say that at each stage you have 4 into 3 to the power n minus 1 new vertices and 4 into 3 to the power n new edges. And now note that whatever words, what are whatever, so calligraph vertices are essentially your group elements, right? And whatever words you are getting are reduced word elements. So for B, suppose your word ended in B, that will go to your A. This will be ending in BA. And so, for example, at this stage, if you see at BA, you will have one going here. That will be BAB, BAA, BAB inverse. But note that we already had an edge here, and that corresponded to the last letter of your word. So let me just erase this to make it more clear. So we already had an edge here because we had to add. So we had to add 3 new vertices. So the one edge corresponded to the fact that that will be the inverse of your last letter, right? So if you have BA here, so there will be one edge labeled A. This will be BA inverse, and so this will be B. So we have already drawn B. So all the new vertices we are adding are just reduced words, in the sense they do not have a inverse in any of the place, right? They do not occur again. So once we have drawn a vertex, the new vertex do not repeat from the past drawn vertices. So since the new, sorry, just a second. Oh my god, right. So since the new added vertices are distinct reduced words in A, comma B, we get that no vertices repeat. Hence, the calligraph is a tree. There are no cycles, because suppose the edges, suppose a vertex repeated, we will get a cycle, but there are no no vertex repetitions. Hence, there are no cycles, and a connected graph with no cycles is a tree. So the calligraph of a free group is a tree. So and we saw that each so this 4 represents a valence. So each vertex is connected to 2 times the number, the cardinality of generator many elements. So that's 2 into 2, 4. So this is an infinite tree. That's how it looks like. So not all edges look the same, in the sense that if you stand at suppose A, right? Sorry, just a second. Suppose let me change my color too. Suppose I stand at my vertex A and consent and start building from A. Suppose I start building the whole tree from A. You will get essentially the same tree. So all edges look the same, but we have just introduced this distortion. So some edges are larger than the other. This distortion is just in our diagram, but as an abstract graphs, each and every edge looks the same. Right. Now, why did we construct calligraphs? We wanted to construct a geometric object such that it had the group as its group of symmetries. So let's see what that group of symmetry. So what does the group of symmetry? So here, this is what calligraph. Let me change the color. So this is calligraph of F2 with respect to the set generating set A comma B. So let's see how. So we know that F2 is exactly the group of symmetries of the tree. This is by the theorem before. Now let's see how these symmetries look like. How does F2 act on your? How do elements of F2 act on your tree? So we constructed calligraphs to get a geometric object which has G as a group of symmetries. So let's look at how the elements of F2 act on the above tree. Right. So let's take any one group element. I'll take A and observe how A acts uh, on your tree. So I want to see how A acts first of all on your vertices. Now, we know that phi A is an action by left multiplication. So let's look at vertices. So let me scroll back. Each and every edge is we are left multiplying by A, right? So one goes to A, So this will go here. Let me erase this all. Right. So 1 goes to A. What about A? A goes to AA. A inverse will go to 1. This will go here. What about B inverse? This will go here. So somehow we are translating here, and there were more, right? So this was like this. We had to add more vertices. So this will go here. This will go here. Here. This will go to the vertex which lies here. Right. Now, so now if a word is starting from A, so suppose the first now we have a left multiplication action, remember. So suppose a word is of this form A B A, then the new word will be of the form A B A. So let's see where that A lies in our tree. So right, so here will be, so this will be A B, this will be what, A, this will be A B inverse, right? Yeah, right. So going from A, any element that starts from A, so this whole region, let me make it better. So this whole region, it starts from A B, A and A B inverse. This will go to the region which starts from A. So that will be, this is carried forward to this region. So so instead of seeing what it does to each and every element, we divide our whole tree into 4 regions. Words that start from words that start from A, words that start from. Let me scroll down. So to see the action of on the tree, it's useful to divide the graph into 4 regions corresponding to the first letter of the word. So so this is the region. So this is the region which has words starting from A. This has words starting from B, A inverse, B inverse. We denote one by a fifth region. So this is a one is a so we add a region 1, the identity element. Now let's see for B. For B, it will be if the word starts from B, it will be AB. Suppose the word starts from B inverse, then the new word will be AB inverse, starting from AB inverse. What about A inverse? Now you have A inverse, and you left multiply by A, then you will get A inverse. So this will be right. Am I audible?
Yeah, you are.
Yes, you are.
Great. It got disconnected. Just a second. I'll stop share. I'll start sharing again. Right. So this A inverse cancels out to the identity element, and whatever remains in the second letter is your first letter now. So suppose this was B, then this will be B, then B inverse, A inverse. But the second letter cannot be A. Why? Why can this second letter not be A? So the setting was that so I was looking at what the left multiplication does to your new elements. I was looking at A inverse and saw that left multiplying by A cancels out this product. So whatever the new word will have, the second letter is the first letter. So and I said this first letter cannot be A. Why cannot it be A? Well, because look here, right? Each new vertex is a distinct reduced word, right? But A inverse A is not reduced already. So we cannot have added A inverse A at any point of the time, right? So if we add A inverse A, it automatically cancels out. That means we already had that vertex before. So This cannot be A. So what does the action of A? So we want to see how does A as a group element act on this, or we want to see what is the phi A of this whole tree. Now we can get a rough description of what phi A does to the graph. So by the above observations, phi A sends, so TA goes to TAA, TB goes to TAB, TB inverse goes to TAB inverse, and 1 goes to A, right? Now TA inverse goes to, so the second letter became a new letter, and the second letter could have been anything except A. So it goes to TA inverse, disjoint union TB inverse, disjoint union TB inverse, sorry, TB, disjoint union 1. So after applying phi A to it, that's what our graph looks like. This will be your phi A of TA inverse. So phi of TA inverse will be essentially this. This is what TA inverse, TB inverse, TB, and 1. So this is just a disjoint union of all the regions. This was TB. This was initially TB. This was TB. So TA inverse, and this was TB inverse, and we had to include the region 1 here, right? And we saw that TA goes to, so this is right. So this is phi TB, right? So this is what, yeah, AB. So this is the region TAB. So similarly, phi of TB inverse, so phi A, it should be phi A, should be equal to uh, TAB inverse. So this region was the one corresponding to the AB inverse. This corresponds to the region A. Now, what can you say about, let me erase the annotation. Now you see that TA inverse, so these four are isomorphic, obviously. TA inverse, TB, TA, and TB inverse. But after applying your phi A, TA inverse goes to the union of these three regions, and your TB goes to this region, this region, and this region. What can you say about phi A of TA inverse versus TA inverse? So this was TA inverse. Note that. Let me draw it by a different color. Initially, this was your TA inverse. Sorry. This was your TA inverse. Right. This was your TA inverse. And now this whole region, the union of these three regions is the image of TA inverse. So what can you say about the size of these two phi? So the image of TA inverse versus TA inverse. Anyone? Is one larger than the other, or are these two the same?
They are also isomorphic, right?
Yeah, correct. They are both of these are isomorphic. Again, that draws back to the fact that all edges look the same. Uh, the distortion is because how we drew the graph, but at every point you can see that. So suppose I consider the graph from this vertex, right? Suppose I consider the graph from, I take the point of view from this vertex. Then from this vertex, this will be your phi A of T inverse. This. This will be the image of TB. This will be image of TA. This will be the image of TB inverse. And you can see basically this is a base vertex, and you have three vertices coming out from this region. And similarly, in your TA inverse, so this was your sorry, so this was your TA inverse, and this is the identity element, not the identity, but the pre-image of your identity element. Uh, and you have three vertices coming out from here, and again you will have these three. So as trees, they are isomorphic. The distortion is just because of how we drew the diagram. So this was a diagram that we considered. Right. So that's how the Cayley graph of a free group looks like. It's a tree. You can generalize this construction and say that the Cayley graph of a free group is a tree, and that's how it acts on your that's how it acts on your that's how if their free group acts on your tree, right? Now, as I mentioned before, just a second. Okay. Here. So, sorry, my bad. The geometric objects we will be considering are graphs and metric spaces. We have considered graphs, but what about metric spaces now? So I hope every one of you is at least familiar with the definition of metric spaces. If anyone has any doubt, you can just speak up. So metric spaces are just a generalization of a notion of a distance. So we introduce a function d, which represents the distance function, and we assign for any two elements of your space x the distance between 2 points. For example, in your real plane, or let's start with the real line. So let me change the color. So suppose this was a real line, and I take 2 points on the real line A and B. So the distance between A and B will be equal to this mod B minus A. That's how we give the Euclidean, the normal distance we work with always. What about R2? Distance between x1 comma y1 and x2 comma y2 by a coordinate formula must be under root of x1 minus, here it should be x1 minus x2 whole square plus y1 minus y2 whole square. Right? This is the whole under root. So we get this examples of metric spaces. This is a Euclidean metric on Rn. So distance between x1 till xn, y1 till yn is essentially xi minus y whole squared. You take the summation, you take the under root. Now I'll introduce two new metrics to you. You may not have seen this before. These two will be very important in our study, but we will like do today. The first metric is the path metric on the graph. So we are given a graph. We want to give the graph a metric. So let T be a connected graph. Note, this graph need not be a Cayley graph or any other special graph. This is just a graph in general. So the path metric on a graph is a connected graph. So we take a connected graph and we define a metric on it. We define a distance function on it. So how can we impose this distance? We can, okay, first of all, I'm imposing the metric, the distance on the vertices of the graph. So what's a natural way of constructing a distance? So suppose I have this graph, right? This, and say this. So I can always take, suppose there one length, suppose there is an edge between two vertices. I can take the length between those two, the distance between those two to be 1. And note, there also exists a path with length 2 between the same two vertices. But we want to consider the shortest such path, right? So I say that the distance I impose the metric by distance between two vertices is the length of the shortest path joining the vertices. So for example, the distance between this point and this point will be, so this will be 1, 2, and 3. Note, it could have been we can have a path with 4 length here, right? 1, 2, 3, 4. But we want the shortest such path, and the shortest such path is 3. So the distance between these two vertices will be 3, and so on and so forth. So distance between any two vertices is the length of the shortest path joining the two vertices. And we saw this idea exactly in the surjectivity part where that we just proved, where we defined the word length to be the shortest edge path between the identity element and the group element. But that was in a very specific setting. That was in a setting of a Cayley graph. But here we want to give a distance function to any graph. So, but the idea is same, that we take the shortest edge path between any 2 points, and we look at the length of that edge path. So we will impose this metric on the graphs many times in the upcoming part that we'll study. So this was the first example. So the path metric on a graph. Of course, you can enforce this path metric on various classes of graphs. So suppose I give you the Cayley graph of some group. You can impose a path metric on that graph. I give you a normal simple graph. Then you can impose a path metric on a graph that turns a graph into a geometric object. It has a metric on it now. Okay. Now next is the group. So this is a very important class of examples. Very, very important. We want to look at the group as a metric space. So I have my setting is that I have a group G and I have S a generating set. We declare the distance between two elements G, H by the word length of, so word length is again same. You can either define it by shortest H path in your calligraph, or you can define it by the smallest n, such that here we want for G inverse S. So G inverse S is equal to S1 multiplied till Sn, right? A multiplication of your you're generating set elements. So the distance between two elements G and H is the word length of G inverse H with respect to the generating set element. This is called the word metric on your group. So for example, I have the identity element, I have say an element S1, so and I have S1 S2. So my the distance between S1 and S1 S2 is essentially equal to 1, because what is this S1 inverse S1 S2, that's in S2, and we only need one element of the generating set to represent it, hence this is 1. The distance between these 2 points, these two elements is 1. Similarly, you can do it for any two elements. You take the element G inverse H and you look at the distance, the word length of that word. This is an algebraic definition. Algebraic uh, definition or algebraic way to represent it. Note the word metric. Now, as you observed before, the word metric on is same as the path metric on a scaly graph, right? Because you had G and you had H. So if you had G inverse H to be S1 till Sn, that means you have an H path like this. So this was S1. The last one is Sn, and the shortest such path, which was a path metric, corresponds to your the smallest such n, such that S1 till such that you have this multiplication S1 till Sn representing that element. This comes from the fact that there was a one-to-one correspondence between the edge paths and the words representing your element. So the word metric on a group is same as the path metric on its calligraph. And we are thinking actually that so note we defined calligraph to be a labeled and directed graph, but we are just thinking of calligraph to be an undirected and unlabeled graph in this situation, that the path metric situation, and we see that these two metric correspond to each other. So that is the distance between two group elements is the length of the shortest edge path between the corresponding vertices in your graph, in your calligraph. Some examples: the word metric on Z with generating set 1 is the same Euclidean metric that Z inherits as a subset of R. So notice, for example, you had the real line, right? So you had this, you had 0, 1, 2, minus 1. Distance between these 2 points is 2 as a Euclidean distance. But also, that this distance is also the same with our word metric. So this makes concrete the fact that I stated that your Cayley graph, since your word metric corresponds with the path metric on its Cayley graph, so this makes concrete the fact that the path that the Cayley graph of Z with respect to 1 looked like the real line. That's what I meant when I said that statement. So the metrics correspond to each other. They impose. And similarly for Z2, there is something called taxicab metric. You can look at it. In summary, this is an important statement. Let me just highlight it. Why not? So a group, uh, a group with a generating set is a metric. Is a metric space. This is an important statement, right? So now that we have a convenient way to see a group as a geometric object, we can start asking various questions like what does a group look like? So you have functions like, we will not discuss these now in our talk, but you can always ask these questions. What does a group look like? Or what is the so how does a group look like at the ends of it? That is, so for example, we had the infinite tree in the Cayley graph of F2, right? So how does what properties can we show for the boundary of your tree? For example, these questions. Or suppose I take a ball around my, suppose I take a random group element and I take a ball around a ball is basically all the elements such that the distance between the group and those elements is less than equal to n. I take such a ball around your G. What elements come under it, and what can you say about these balls, and so on. So there is something called isoperimetric functions, and there's something also you can sometimes embed your. So okay, let me not mention that. So yeah, so the you can always ask questions like this, like what is the length of a curve, or what's the shortest distance joining 2 points, or something so forth. Now, as before, continuing our theme, we mentioned the geometric object. We look at its symmetries, isometries here. Isometries of a metric space are basically a bijection which preserves the distance, which preserves the structure, that is f from x to x, a bijection such that distance between fx and fy is same as distance between x and y. So set of isometries form a group, and we denote it by isom of x, isometries of x. And this is a group of symmetries of a metric space. For example, automorphism of T was the group of symmetries for a group. This isom of x is a group of symmetries, for a graph. And this is a group of symmetries for a metric space. So some examples are translations in Rn, rotation about a point in Rn. So suppose I take the R2, I rotate everything along this path, along this direction, right? I rotate everything 90 degree. Then that's an isometry. It's a bijection and it preserves the distances, right? And again, we want to look at group action on metric spaces. Again, it's an homomorphism from G to isometry of X. So it's an action, a normal action, plus it preserves the distances. It preserves the structure. So because of this, a homomorphism G to isometries of X. So each G gives rise to an isometry of X. Again, we can denote it by phi of G. So suppose you add a homomorphism G to out of T. In case of your graphs, then each element of G corresponded to a automorphism of a graph. Here, each element of G corresponds to an isometry of X because we have a group action on metric spaces. Note this is equivalent to, so first two, these three definitions, so these three are essentially, so these three are essentially a normal action. Oh, I've already written it here. So these are action on X. So we want to impose the extra condition that distance of g dot x and g dot y is same as distance of x comma y. So it preserves the distance. So this is once we impose this condition, we mean that the action is by isometries. That each g gives rise to a isometry of your space x, metric space x. For example, D2n acts by isometries on n-gon in plane. Now, in plane means that you are giving distance between every point. Previously, we did not explicitly mention this, but we kind of assumed it. But yeah, so now this is your xy plane. Sorry, this is your xy plane. This is your 1 comma 1 and so on. So what 1 minus 1? Sorry, 1 comma minus 1, I guess. Yeah. Right, and so on. So this is a plane. So so D2n acts by isometries. So acts on an n-gon. This is a normal D2n action of a group on a set, and we are adding the condition that it's by isometry. So it preserves the distances. Z mod nz. So given R2, as I said, the rotate about the center by 2 pi by n. So Z mod nz acts by isometries on R2 by rotations. So this, for example, if we see the orbit of this point, so this was what 1 comma 0. This goes here, suppose by rotations, you get an n1. The orbit of any point is an n1. Every group acts by isometries on itself. So we take G with word metric. So this is a metric space, and we let G act on itself by left multiplication. We already had that action. And of course, you can always have a trivial action, G on every metric space given by G dot x is defined to be x. So G dot x is defined to be x for all G belonging to G and x belonging to x. That's a trivial action. That is, for all G, all G fix all the point of x, all the points of X. But we can see this action is not useful, this is trivial action. Why? Because essentially at G fixes all the elements or all the points of X. So when do we get more info? We get more info when most elements of G actually do something to your metric space, right? So when the kernel is as small as possible, that is the most of the elements of G actually do something to the plane that is there, that they do not have a trivial action, right? Now, so that's why most of the theorems we study consider free actions. So because it's the best possible case scenario, they give the most information. Free action gives you the most information about a group action, since most of the group elements are acting somehow on your space X. Now, till now what we have done is we associated a geometric object with your group. But what do we do with it? We want to extract some algebraic information about the group using the geometry of your geometric object. So we go from geometry to algebra. So we want to translate your facts in geometry, how things interact in your geometric object, which is related to your group, and we want to see what does it mean to the group. What does it mean in algebraic sense? So that this is an important part, and that's what we are gonna do the most of the rest of the this lecture and the next lecture. We want to see that how these geometric objects, the geometric properties of these objects, how do they translate to your algebraic sense, right? So till now we have seen that group acts on a geometric object, but how do we utilize this fact? So this theorem essentially shows the power of applying geometry to algebra. So this theorem shows that how we can tell something about the group by studying the geometric object. So some definition first. So given a group, a torsion element of a group is an element with a finite order. So finite order means, so torsion element is an element G such that G to the power M or G, so the operation applied to G M times is equal to the identity element. This is called the, this means that G has finite order. So this is the order of your element G. So a torsion element is one with finite order. Note the identity element always has a finite order because id to the power 1 is equal to identity. So G is torsion free if and only if, no, sorry, not if and only if. Oh, yeah, that's the definition. I mean, if and only if would work. So D is torsion free if the only torsion element is the identity element. We want that no other group element should have a finite order. So the theorem is, suppose G is a group. Suppose G is a group that has a free action. So as I said, free action because it extracts the most information. So suppose it has a free action by isometries on Rn. So we have a free action by isometries on Rn, and we equip the Rn with Euclidean metric. Then G is torsion free. That is, G does not have any finite order element. Now this is a purely algebraic fact. And this free action, this is a geometric fact. So we want to show that a free action by isometries on Rn would mean G is torsion free. Some example, of course. First of all, let's look at Z. As it's first going to, then I'll give you some nice examples. So I want to prove that G is a group and it has a free action by isometries is basically means again the same thing. It's an action on a metric space, so it's a normal action plus it preserves the distances and it's free. I'll remind you what's the definition of free action. So free action basically means only identity fixes an element. That is, G dot X is equal to X implies G equal to E. So any non-trivial element does not fix any element. So we have so each and every element of the group does something to your metric space, and the metric space here is your Rn with Euclidean metric. So now we want to prove that G is torsion free. Right, let's try to prove it. Just a second, I'll switch back to my Wi-Fi. My electricity had gone, so I'd switch to my hotspot. Just a second. Right. Okay, so also this theorem essentially typifies the theme of the geometric group theory subject. So it uses the interplay between G and so this theorem uses the interplay between G and the metric space Rn in order to gain purely algebraic information about G, which is that G is torsion free. So proof. Let's try to prove it. Sorry. So what do we have? I have so let's prove by contradiction. So suppose G was in G, and suppose G had a finite order, or G to the power m is equal to identity element. So I'll use one for the identity. So suppose this. Now, so let's look at the subgroup generated by G, which is equal to G. This is G square 1 G square G cube till you'll get G to the power n minus 1, and the next one will be G to the power m, so which will be just your 1 again, right? So this is the subgroup generated by G, which is 1 G square G cube till G to the power m minus 1, and the next one will just be G to the power m, which is 1. Now let's look at how so let V belong to Rn, right? So let's take a point in Rn, and let's look at how this subgroup acts on your. So let's look at how all these elements act on your V, right? So we want to look at how does this act on V. So this will be essentially equal to V G dot V till G to the power m minus 1 dot V. Note, we do not have a specific, we do not have a, V is just a point in Rn. We do not have some multiplication going on here. This is just the group action notation. So G dot V. Now, notice, what does, okay, so let's call this O. This is set O. So basically, mod G dot V is equal to O, and that's equal to V G dot V till G to the power m minus 1 dot V. Let's look at what is G dot O. What is G dot O? So we have G dot V, then we'll have G dot V, that's G square dot V, and then we'll have G to the power m minus 1 into V, so that's G into this, so that's G to the power m dot V. This is equal to 1 dot V is equal to V. So rearranging it, we get V, G dot V, G square V, until G to the power m minus 1 dot V. So note, this is again equal to O, right? So G acting on your orbit is essentially equal to your again equal to your orbit. Now we want to prove that so what do we want to have some contradiction, right? How does that contradiction arrive? Note, so note to each set. So suppose you have a set O, right? Suppose you have a finite set in Rn. Look at its set right. Look at its set right. So this is a unique point in Rn, such that the distances, so such that sum of distances to the elements of your finite set to points in finite set is minimized. So this centroid is essentially a unique point in Rn. A unique is important. So a unique point in Rn such that the distance between the points between the point to the centroid is minimized. So let me draw the diagram. So this is, say, let's look at R2 for example, because it's easier to visualize here. We took this to be the V. We looked at, suppose this was GB, G square V, and so on. And here was G per M minus 1B. Sorry. Yeah, this was your R2, this was V, GV, G2V. Now, what we did was, and of course, to all these, there is in R2, for example, here, this is the centroid of this finite set. But applying G to this new diagram here, so apply G to this whole diagram you have now. That's what we did. This finite set was O, we applied G to O, so we get that. Now this V goes to G. This G to the power M minus 1 into V goes to V, because G to the power M was essentially E. So we again observed that this was G dot V, so V, GV, and so on. We again got the same set, the same finite set. That means it's again the centroid is equal. So if that was W, this should also be W, because both the sets are equal and there is a unique centroid. But in between we applied G, right? So essentially W should have been carried to G dot W. So W carried to G dot W, but since this finite set remained the same, hence the centroid remained the same. We got at this point is also W. That implies G dot W is equal to W. But because it's a free action, what does a free action mean? If GW equal to W, that means G equal to E. So the only torsion element, the only element with a finite order is the identity element. So that's how we extract the geometric information using the centroid here. And so I'll repeat the proof. I take this point V and I look at its orbit. So V, GV, G square V, G cube V. We go on to G to the power M minus 1V. And if we apply G, one more, so next will be G to the power M into V, but G to the power M is E. So that would again give you a V again. So you get a finite set V, GV, G square V, and to that you have associated a centroid. That is your W here. So this is your W. Change my color. And here, now what you do, by applying, because essentially V, GV, G square V, and G to the power M minus V goes to G to the power M into V, which is essentially V. So your finite set remains the same. That means your centroid remains the same. But since you applied G to it, your because the action that means G dot W means equal to identity element. So that's how we prove the theorem. That just a second. That if G is a group that has a free action, so we use free. We have used this fact. Yes. It's action by isometrics we have used on Rn. So we have extracted a purely algebraic fact about our group G using only the properties of your action. So does anyone have any doubts in this proof? Anyone? So I'll assume it's clear to everyone. There is only one point that needs resolving. That's this. For every finite set that you have a unique point called centroid. So that's your exercise. Prove any finite set in Rn has a unique centroid. How you would prove it is, so hint, use that. So use this fact: sum of convex functions is convex. and then use the fact that convex functions have a unique minimum. So this uniqueness would give you the uniqueness of your centroid. So just a small exercise that for any finite set in Rn, you have a unique centroid, and the whole proof will be uh, should be very clear to you. Right. So basically till now, let me add a page and switch back my color. Also, how much time do I have left? Anyone? Uh, Snain, are you there?
Yes, Harshul.
Yeah.
Yeah.
So how much time do I have left? 20, 25 minutes?
It would be better if you could conclude by 3:30.
3:30. Okay, I'll try to do it in 10-15
Yep.
minutes. All right. So now basically, what we have discussed till now is we have a group, we have a geometric object, and we saw how these two interact with each other, right? So now the question to ask in geometric group theory is essentially, so this is the main question we consider in geometric group theory. Which groups act by isometries on which spaces? And then you ask, if a group does act on a space, if a group does act on a space, what does it say about the group? And what does it say about the space? So also one more thing, that if we think uh, about a group as a metric space, that is the word with the word metric, what does the group look like? So these are the main questions we ask in geometric group theory. So we already see an example in your previous theorem, that so we already saw an example of this space which group acts by asymmetries on which if a group does act on a space, what does it say about the group? We already saw an example of this in form of theorem that says that if you have a free action by isometries on your Rn, then G is torsion free. There are no finite order elements. And yeah, so one more. So the next question that we will consider in this line, that if a group does act on a space, what did it say about this group? So today, some part of today, like the remaining 10-15 minutes, and tomorrow, we will move along this line and prove the following theorem. This is a very strong theorem. I mentioned it yesterday too. If a group acts freely, uh, acts freely on a tree. So a tree, remember, a graph without connected graph without cycles, and it acts freely on a tree. It gives us the most information about the group. That implies the group is actually free. The group is a free group. That's a very strong theorem. A corollary of this would be, so once we have proved this theorem, we will get a corollary that, suppose, yeah, again, as I said before, if G acts on a space, then a subgroup of G or H also acts on a space. So suppose the action was of G freely on the tree T. That implies H also, H is a subgroup of G, also acts freely on a tree T. That means H is also a free group. This implies the corollary is subgroups of free groups are free groups. This is a very hard algebra, not very hard, but it requires some difficult mathematics to prove this theorem that subgroups of free groups are free groups using only algebra. If you use only algebra, you'll see that it's a very difficult proof. It's a very involved proof. It involves some good amount of work. But in geometry, so for example, if you involve some topology or some geometry in it, you can resolve this question easily. So this is what we aim to do uh, today and the next 5 minutes, and let's do it tomorrow itself. I'll mention one or two more theorems that I'll not prove here, but there are they follow the same theme uh, of looking at groups and their actions. So a theorem is basically what we want to do is from just the information that a group acts on a certain kind of space in a certain way, we deduce some concrete algebraic information about the group, right? So here is a theorem. So for example, I said that the Cayley graphs are roughly the same in the sense that so now you can make that precise. You can give the two Cayley graphs of a group with respect to different generating sets are roughly the same. So basically that means if you give them the path metric, then up to some scaling and up to some maximizing and zooming in and zooming out, those two are remain within each other's distance. So that's called quasi-isometric. That two spaces are quasi-isometric if they are roughly close to each other. Two metric spaces. So up to a minimizing constant and up to a scaling constant, those two remain the same. So this is a theorem. As I have not defined quasi-isometry properly, I'll not prove this theorem, but this is a good theorem to know. So if a group is quasi-isometric, this is quasi-isometric to Z, to the real line. So for example, you had that. So some examples would be the Cayley. So Z with some different generating sets. So Z, 2, 3, or Z with n, n where m and n are GCD have GCD1. So if a group is quasi-isometric to Z, then it has a subgroup. It has a subgroup of finite index that is isomorphic to Z. Right. So geometric theory is full of these theorems relating geometry to by relating these group actions, this geometric properties to your algebraic properties, and yeah. So we basically want to. I'll take 5 more minutes. So we basically want to start proving this theorem. So instead of starting to prove this theorem, I'll give you an example first and convince you that yes, this theorem is actually useful. So we want to prove that. So this is the theorem we are set out to prove is that. So suppose G on a tree T, then G is a free group. So I assume so. So GL, this is a group of matrices. Group of matrices with determinant not equal to 0, 2 cross 2 matrices, and entries are from Z. Entries are from Z. For example, 1 0 0 1, 1 0 1 1, these are, and 2 5 3 would have been sure, 6 would do, right? Right. Something. So all matrices of this form a group, and SL I've defined it has a subgroup SL to Z. This is all the again the same group SL, but we enforce a restriction that determinant of all such of all matrices from this subgroup is equal to 1. So again, the group of 2 cross 2 matrices with entries from Z, but the determinant should be 1. This is a subgroup of the above, GL to Z. So this will include something like 1001 and this 1011. This will not be included. Now, SL2Z is not a free group, but now we can give a, so look at this map. So first of all, first SL2Z is not a free group. Why? Because it has elements of finite order. But a free group cannot have, because there is no relation between the elements or on the elements on the generator itself. There are no finite order elements. So because it has elements of finite order, find them, of course, not equal to ones which are not equal to identity. However, SL2Z has subgroups of finite index which are isomorphic to a free group. What are these groups? So these groups are basically, so consider this. So I take the map SL2Z to SL2ZM. So this is everything but with mod M. So something like if I take M to be 3, for example, M to be 3, then 4217, that's a 81, right? That works, right? That's a SL2Z. Then mod 3, this will essentially be 1. Oh, this is 1, 1, 1 minus 1, right? Or 2. We are taking everything mod 3. We are giving a map, a surjective map from SL2Z to SL2ZM. And we have a kernel of this. So this has a kernel. Sorry. Sorry. My bad. I wanted to say Z mod MZ. This. And this has a kernel. So kernel means elements here, the 2 cross 2 matrices with determinant 1 here, which go to the identity element here, which go to the 1001 here. So for example, 4004. This will be in the kernel because taking mod 3, it goes to 1001. So I denote the kernel by Z and M. I just denote that kernel by this. So this is a group of 2 cross 2 integral matrices that have determinant 1 and that are equal to identity matrix modulo M, right? So this subgroup is actually called level M congruence subgroup of SL2Z. So this first of all, this has a finite index in SL2Z. Why? Because by first isomorphism theorem, this should follow SL2Z, the index of SL2Z to SL2Z M should be equal to, by first isomorphism theorem, equal to SL2 Z mod MZ. And since in this each element of your matrix, each one of your 4 entries has finitely many choices, M choices. So there can be at most M to the power 4 matrices, and out of which, of course, you can even restrict it because the determinant is 1. So that means this is finite. This means that it has a finite index. We will prove. Okay, let me change the page, or actually just do it here. We will prove for M greater than equal to 3, SL2ZM is isomorphic to a free group. Isomorphic to a free group. How we will do this? We will apply the theorem. So this is a good application of the theorem. We will apply this theorem and we will give a tree that SL2ZM acts on freely. Then we will conclude that G is a free group. And this tree will be is very occurring in mathematics. Like you will encounter this, the tree we will introduce in various parts of mathematics and very frequently. So yeah, it's called Faraday tree. So uh, it's called Faraday tree. Faraday tree. And so that's what we will look at tomorrow, the proof of that theorem, and how to prove that, and we will prove that SL2ZM is isomorphic to a free group by showing that it acts freely on a Faraday tree. We will prove, first show, I'll tell you what a Faraday tree is, and then tell you about the SL2ZM. And one more thing to mention. So sometimes you don't get this condition called freely, G acting freely. However, you get some some not that strong, not this strong of a condition, but some less strong conditions, but using which, so if it's isomorphic to a free group, you're essentially giving it a presentation, right? It's modest and there are no relators. But if it acts it acts less restricted than or more restricted actually than freely. The action is less more restricted than free action. So I don't know. It should be less restricted or more restricted. Basically, you don't have as much information, but still you can do some good amount of work, and you have to prove you get to prove. So SL2Z does not act not it does not act freely on your Faraday tree. We will prove this, but still there it satisfies some condition. We will mention it tomorrow. And using that condition, you can tell that SL2Z has this presentation. You can actually give the presentation of SL2Z, a comma b, given a to the power 4 equal to b to the power 6 equal to identity, comma a square equal to b cubed. SL2Z is isomorphic to this presentation. You can prove this fact by looking at that same action. It will not be a free action, but it will still give you some information. So yeah, that's it for today. Thank you for attending. If you have any doubts, you can just unmute yourself and. I'll share this PDF on Discord. You can have a look and ask some questions. Do attempt the exercises I've given. There's essentially only one exercise that finite set has a centroid, right? So try proving that, and yeah, that's it. Thank you, everyone.
Thank you, Harshul.